What's up, YouTube? Welcome to Benzene Chemistry. In today's reaction, we'll be seeing Finkelstein's reaction, which allows you to switch from one halogen to another on your sp3 hybridized carbon. So it's a nucleophilic reaction of order 2. And we'll see the mechanism, and we'll check out a kinetic study to see what parameters influence SN2 reactions the most. And also we'll check the usage of such a reaction. So when you have an SN2 reaction, you have your nucleophile that attacks a carbon that has a leaving group on it. In this case, the leaving group and your nucleophile are both halogens. So the halogen that you want to implant on your molecule, in this case the pink one, would attack on your sigma anti-bonding orbital, and it would eject your other halogen as your leaving group, and it passes via this intermediate state where this bond is being formed and this bond is being broken. So you form the one in pink and you break the one between the carbon and the green halogen. And this reaction is reversible because sometimes the energy differences between your product with one halogen and the one with the other aren't too different, so you could have the reverse reaction happening because the activation energies aren't too different in some cases. But we'll see soon enough how to drive the reaction towards the product that you actually want. You also want to consider the ability to be a leaving group of each halogen, and also the nucleophilicity, and we'll check out these three aspects in details. You need to consider two things about your carbon halogen bond. So first of all, its strength. So if you have a bond that's too strong, like carbon and fluorine, it won't budge, it won't break, and you won't be able to substitute it even with a strong nucleophile. So SN2s are rarely observed using fluorine on your original alkyl. Instead, most of the time what you'll see are these three, which are better leaving groups, and it's not only due to the electronegativity of those, because you could say that fluorine is more electronegative, hence it would prefer to have a negative charge on it because it's really close to the core of your atom, so it could stabilize it a bit better. But in this case, it's about the size of the actual halogen in its negative form, because like I said, the carbon fluorine bond, you just won't break it. So you need to consider these two, the size and the bond strength. So let's just quickly check the sizes. So the bigger the atomic number is, the better your leaving group will be. And if you do a quick linear combination of atomic orbitals according to hydrogen, you get something like this. And you can see that as you go down your halogen column on the periodic table, your atomic number goes up, and this also means that the orbitals are further and further away from the core. And the better leaving groups are the ones that have the bigger volume. And of course, when you reach bromine, you also need to include your d orbitals from these 10 electrons. So you have 5 new orbitals to put. I wanted to sketch this just so you can see how it gets bigger and bigger. And I didn't do iodine because it was too much, but you get it. It gets bigger and bigger, and the bigger it is, the better it is as a leaving group for halogens. Just to clarify something that I wasn't quite satisfied, I just said that HF was stronger than HI. I know it's not because of electronegativity, and it's the same reasoning that I minus is or iodide is more stable than fluoride, and HF is stronger, but it's not for the same reason. It's because it's a superacid, and that's a different topic. But I minus is more stable as a leaving group, and you can kind of think of it like with resonance. You can say that an acid, that when it dissociates the negative charge formed is spread by resonance, you can say that this acid is strong, right? Because the conjugate base is stabilized. So when you have your leaving group, you can say that it's stabilized because it's spread throughout a bigger volume and a bigger surface. So you can kind of think of it that way, but instead of being spread around a few atoms, it's spread around a bigger distance. There's a bigger surface, bigger volume, so it makes it a better leaving group. Another important aspect when you do an SN2 reaction is to choose the best type of nucleophile, or the nucleophilicity, in this case, of your halogen. And this depends, in this case, of your solvent, because if you have a F minus of fluoride atom, it can do hydrogen bonds with water, whatever. It can do hydrogen bonds which lower the energy of its lone pair of electrons, making it less likely to attack your carbon instead. And in polar product solvent, where you have the possibility to do these hydrogen bonds, then the one that's less likely to do hydrogen bonds is the one, like I said, that has the bigger volume. The charge is spread through a large surface, and it's less likely to do hydrogen bond, and then the lone pair of electron can actually attack your carbon. So in polar product solvent like water, acetic acid, or methanol, then your iodide is actually your better nucleophile, because all of the other ones are better at making hydrogen bonds. And when you don't have that interaction of hydrogen bond, then it goes with the normal trend of electronegativity. So fluoride being the best nucleophile in polar product solvent. Before going to the next important aspect of an SN2, let's quickly review the energy diagram for this one, which is typical of an SN2 reaction. So you start with your first halogen, to which you add your pink halogen in the mix. It attacks. You overcome a certain activation energy, and you reach your final product with your pink halogen on it. And if your pink halogen carbon bond is stronger than the one you had originally with the green halogen, then your reaction will be exothermic. Since this one is more stable and lower in energy, and this one was less stable because the bond was weaker, so it was more reactive and it's higher in energy. And if you want to take a look at how spontaneous the reaction is, you need to use Gibbs free energy, which is given to you by this for Gibbs free energy. And in this case, you have two molecules at first, because you have your first halogen, it attacks, and then you release the other halogen. So you have two molecules on each side, so the entropy change isn't a thing. So you can basically erase this term. So if you want a spontaneous reaction, it needs to be exergonic. So your Gibbs free energy is below 0. Like I said at the start, this reaction is reversible. So the reverse reaction is actually possible, where your green halogen, this one, would go back and attack, and then you get this one with your pink halogen being ejected. Then it goes back and goes back. So you end up with a ratio that depends on your equilibrium constant. And this is a thermodynamic control. So you'd end up with more of this one than this one, because it's more stable. But you still get some of this one. So if you want to optimize how you convert it, there's some tweaks, and we'll see that just now. Like I said, the reaction's reversible. And you might be thinking, how is the conversion or the yield any good for a reaction that's reversible in thermodynamic control with product with such similar energies? And you're right, because if you have, for example, chlorine and bromine, they're not that different in energies, and the reverse reaction can actually occur quite a lot. So your ratio at the end would be not the greatest. But one way to tweak this reaction into making it have full or almost full conversion is to make it irreversible. So you basically stop the reverse reaction from happening, and it allows you to reach better conversions and better yields. And if you want a thermodynamic argument to back that off, you can talk about chemical potential. And basically, we said that the variation of Gibbs free energy was below zero, right? So if you plot it during your reaction, the Gibbs free energy goes down eventually. And at some point, it stops going down and it reaches a flat part where you can say that it reached equilibrium. This is at constant T and P, temperature and pressure. And if you look up in your physical chemistry textbook, you can find this equation for a material equilibrium at a PV only situation where the only types of work would be related to pressure and volume. This doesn't concern us because we're pretending we're at constant temperature and at constant pressure. So once you reach equilibrium, you're also at constant Gibbs free energy. So you can say this, and you find that at equilibrium, all of your chemical potentials must be equal to one another or equal to zero. So as long as you keep removing some of the reactant or the product, then you can't reach zero because this equation won't be true, and the system will tend to try and stabilize it to eventually reach the point where the minimum Gibbs free energy is reached, and that's when you reach equilibrium. And when you keep removing it, you force the equilibrium to be further away in the direction that you want it to be. So you force your reaction to be complete or to have better conversion. So this is basically a fancy way of explaining Le Chatelier's principle, which you're probably familiar with if you're watching an organic chemistry video. So basically, if you keep taking off some weight off the balance of Le Chatelier, you can see it as you want, then you have to keep reacting, to remove weight from this side as well. So if you keep removing products from one side of the reaction, then your reactant will have to keep on reacting to create more products. And this is pretty common. And in this Finkelstein's reaction, you do it by using solubility differences. So one of the salts that you're using precipitates. For example, you can use, if you want to add an iodine to your carbon atom, if you want to use iodine to do a nucleophilic substitution, like Finkelstein, you dissolve it in acetone with your alkyl, your halogen alkyl, and when it reacts, it creates the other salt that is now insoluble. And since it's insoluble, it's like if your change in material keeps on changing, because your system wants to form more sodium bromide as to lower your Gibbs free energy even more, according to your equilibrium condition. So if it wants to reach the bottom of your equilibrium, of your Gibbs free energy diagram, then it needs to convert it as to reach the equilibrium condition where you've minimized your Gibbs free energy and all of the chemical potentials times their change in material are equal. So when you keep removing your sodium bromide, then the reaction keeps on going towards the side that you actually want it. So that's how you tweak or optimize your conversion in any kind of reaction that uses this, including Finkelstein's. So I said this was an SN2 reaction, and one way to prove it is to look at the kinetics of the reaction, so the rate of reaction, and it's an SN2 because it's of order 2. When you had an SN1, the only component that mattered was your carbocation, and in this case, both substituents matter, so your halogen and your halogen alkyl. In this one, they use sodium iodide salt, and they made it precipitate in acetone, like I just talked about. using Le Chatelier's principle as to drive the reaction, and they measured the speeds, the rates of their reaction by using by measuring the conductivity from electrical conductance. So we'll talk about this, but the general kinetic equation is this. So your rate constant multiplied by your two components. You have this, and your rate can be linked to your rate constant. Sorry, can be linked to the activation energy from this equation, Arrhenius' equation. And now we're interested in this part of the energy diagram, the energy of the activation energy. So this is what matters. When I talked about earlier, I mostly talked about the difference between these, so as to make the reaction spontaneous. But now what matters is the energy of activation, because we're measuring rate constants, which are linked to it directly with Arrhenius. So yeah, they measured the conductivity from electrical conductance, which is the inverse of the resistance of your solution, which you can also link to conductivity. This is kappa. It might be confusing because there's a bunch of K's, but this is kappa. I'm just not that great to write kappas. And yeah, and this is linked to the electrode properties. But basically, they use the fact that the conductivity is proportional to the square root of the iodized salt. And they were able to do those graphs where it's 1 over the concentration of your iodized salt, and it increased over time, and they measured with that the difference in the concentration of their salt, and with that they were able to measure their constants because they knew the starting amount of salt and how it disappeared, and you know it's 1 for 1, so you can directly obtain your rate constants from that. They also measured, I think, the activation energy. I should move using Arrhenius too, because you can plot it in this way so that you can use different temperatures to find the slope, and your slope gives you your activation energy. Just for fun. So yeah, they tracked different parameters and how it impacted the speed of the reaction. So how important some aspects were, because sometimes your reaction is supposed to occur, but it occurs so slowly that you won't ever get your product. So you need to consider kinetics if you're actually doing it in the lab. In theory, you can check the final and the final energy and the starting energy, but when you actually want to do it, you want it to take a reasonable amount of time. So you need to consider those aspects. So the first one would be that you have a good leaving group, like we talked about. So the rate constants varied by 328 times when you have a bromine atom versus a chlorine atom. Like we said, the bromine atom is much more fat or whatever. It has more volume, so it's a better leaving group. So this reaction occurs much faster than this one. Another important factor is steric hindrance. They measured that the rate constants differ by 58 times when you have a terminal versus a secondary halogen. So this is because the transition states aren't at the same energy, because one has more repulsion than the other and is more hindered. So if you have your terminal, yes, you have this that could freely rotate and come near the iodine, but it's not as bad as having two sites where you have hindrance. So this one would be higher in energy, so it would be somewhere around there. So the activation energy for this one would be much higher than the one where it's a terminal halogen. So yeah, 58 times, so quite the important factor. So last and kind of the least important parameter is the solvent type for this one. Sometimes it's very important when you have a charged intermediate, or yeah, I think that's the case. That's where it impacts the most. But in this case, it's not really charged. There's some partial charge, so I guess that's why it varies with your solvent. And in your, depending on your dielectric constant, I guess you can vary the activation energy. I'm not sure how to explain this one because you have salts at the beginning and the end, and the transition state isn't charged. So I'm not sure, but yeah, this is the least important type of parameter to impact the rate constants. So when do you actually use Finkelstein's reaction? Some reactions are very not fancy but picky on the halogen that they need for them to work. And certain types of couplings, I know that you need a specific halogen, so sometimes you need to switch it. And you need to be sure that it's an sp3 hybridized carbon, because it's an SN2, so if it's an sp2, for example, it won't work. Like if you're doing a coupling on an aromatic, you can't use Finkelstein's because it's an sp2 carbon. But yeah, basically for some couplings, and if you want to change the reactivity of your molecule in regards of the leaving group, then you can switch halogens. If your leaving group is not reacting enough or too much, then you can switch halogens using Finkelstein's, which can be used to get pretty good yields. And you can also switch it for electronic reasons. Sometimes one halogen withdraws too much or not enough, so you might want to switch it. And sometimes you buy a commercially available product and it has a chloride on it or chlorine, and you want another halogen for X or X reason. So Finkelstein's a good way to switch it. So that's about it for Finkelstein's. This video was a bit different from the others. I went a bit less into the synthesis part and a bit more into the details. I wanted to do a simpler reaction just to get a chance to explain the basics in one video. Gotta start somewhere, you know. So I hope you guys enjoyed. If it helped you, I'm happy. And you guys have a good one. See ya.